Hey everyone. In this video, we're going to start to look at the last major model that we're going to see in this course. Now, before I introduce this model, I want to point something out. While this model may be new, it's not all new. A lot of the things that we've already learned in this course are going to apply to this model, just as they've applied to every other model. For example, the law of conservation of energy, which we've seen throughout this entire course, still applies here. It's just that we're going to see it in a slightly different form. The model that I'm talking about is called the model of thermodynamics. Now, the model of thermodynamics is extremely general. It shows up all over the place. But for our purposes, the model of thermodynamics is a model that describes how gases behave. Well, why gases? Let's think about the particle model of thermal energy that we learned about last week. We saw that solids and liquids always have 6 modes, 6 degrees of freedom, and that allows us to calculate the amount of thermal energy that they have. This is not particularly interesting. The number of modes is just 6 all the time. But gases are more complicated. Gases can have many different numbers of modes, depending on how many atoms are in each particle and the shape. Gases are also different from solids and liquids in another interesting way. You may have heard that a gas will always fill up the entire container that it's provided. Gas has no fixed volume. The volume of a gas can expand and contract depending on the situation that the gas finds itself in. Solids and liquids are not like this. While their volumes can change a little bit depending on their temperature, it's pretty minor. Whereas gases can have huge changes in their volume just depending on how much energy has been added or removed from them. For that reason, we need a whole separate model that can describe this behavior and allow us to make predictions about how gases will behave. Now, gases require us to think about 2 quantities that we really haven't seen much in this course: pressure and volume. Volume is the easy one. It's just the amount of space that the gas takes up. Volume is measured in meters cubed, but you can also measure it in ounces, cups, cubic feet, whatever. But again, for our purposes, the measure of volume will be cubic meters. A cubic meter is just a box that's 1 meter on each side, 1 meter wide, 1 meter tall, and 1 meter deep. The other quantity that's important for gases is pressure. Now, we're not going to talk too terribly much about pressure and what it does in this course, but you can sort of think of pressure as just a description of how much the gas is pushing on its container. The higher a pressure, the stronger the container has to be in order to keep the gas in. In principle, if you raise the pressure high enough, the container will just explode, like a balloon that has been overfilled. We're not going to study that in this course. In our models, the gas will always be in a container that can handle whatever the gas chooses to do. Now, there are 2 main kinds of systems that we're going to study in this course. The first is systems that have a constant volume. These kinds of systems are just gases that are inside some sort of rigid box. The box cannot get bigger or smaller, and so the gas must always stay at the same volume. But we're also going to look at gases that are in flexible containers, containers that can sort of expand and contract with the gas. The classic example of this is a balloon. You may not have done this experiment before, but if you put some air in a balloon and then allow the air to be warmed up without, of course, bursting the balloon, the size of the balloon will actually increase. The gas is expanding its volume as energy is added to it, and that causes the balloon to expand as well. An expansion like this is what we think of in thermodynamics as a process. Now, in this course, we've actually learned about processes and states quite a bit, even if we haven't thought about them in those terms. A state is just what the system is doing at a very particular moment in time. The example that we've seen a lot is a falling object. When this object falls, it goes from one state where it's being held up here to another state where it's close to the ground. These states are connected by processes. In this case, the process is just the object falling. With gases, it's similar. A state is just something that you can measure about the gas at a very particular point in time. And a process is just something that takes your gas from one state to another state. Of course, along a process, there are a bunch of individual states that may or may not be interesting. But often, at least in terms of energy interaction, the details of what's happening during the process are not totally critical. We can sort of think more about one state and the other state and get a lot of interesting results. But there is one or two things that do matter when we're talking about processes. A really good example is heat. Heat is always something that we talk about in a process. For example, it doesn't make sense to say what is the heat that an object has at a particular moment in time. We only ever talk about the heat that enters or leaves something as it moves from one state to another, as it goes through a process. The same thing is true with gases. Heat is just something that goes into or out of the gas during a process. The same is true with work. Now, we'll see how work comes into play when we're talking about gases in the next video. But the key thing to remember here is that heat and work are more or less just the same thing that they've always been. They're just ways for the total energy of the gas to change. We have an equation for this in thermodynamics. It looks like this. Now, maybe you don't recognize this equation, but it's actually the same energy interaction equation that we know and love. U in thermodynamics just means the total internal energy of a system. Q and W are just heat and work, as they've always been. So this equation just says that the change in the total internal energy of a system is equal to the heat that goes in or out plus the work that's done on or by the system. Again, this is just the exact same thing that we've always seen. But in the case of thermodynamics, we're only talking about a particular kind of energy. We're talking about the internal energy of a gas. We're never going to see a case where we have a box of gas that's flying across the room. We're always just interested in thermal and bond energies. But for gases, we don't even need to think about bond energy. As we learned last week in the particle model of bond energy, gases have no bond energy. So for our purposes, we're always going to be talking about gases that are well above their phase change temperature. They're never changing phase, they're only changing their temperature. And so when we have this equation that the change in internal energy is equal to the heat plus the work, what this equation really is saying is that the change in the thermal energy of the gas is equal to the heat plus the work. The model of thermodynamics is useful when talking about very large numbers of particles. If you're only thinking about a few particles, then you really need to be using the particle model of thermal and bond energy to make sense of what happens. So why did we spend all that time on the particle model of thermal energy if we're not actually going to use it in thermodynamics? We actually are going to use it a bit in thermodynamics. The particle model of thermal energy allows us to quantify how much a gas is going to change its temperature depending on the number of modes that each particle has. This is still useful information. In the particle model of thermodynamics, we may still need to know how many total modes that our system has. This will allow us to calculate the heat capacity of the gas, which will allow us to understand how its temperature is going to change as energy is added or removed. So even though we're not going to spend a ton of time thinking about individual particles anymore, knowing how many modes a single particle in a gas has, and therefore how many modes the whole gas has, does allow us to understand things about the thermal energy that we will need to know in order to analyze a system using the model of thermodynamics. But before we turn our attention to the behavior of the gas, we need to know one other little thing. As I mentioned earlier, we need to know what work means in the context of a gas. If you'll recall, work happens when an object is feeling a force while it's moving. But I already mentioned that we're not really interested in the kinetic energy of the entire box of gas when we're thinking about the model of thermodynamics. This is true, but there actually is a way in which we can think about work when we're talking about gases. Work comes into play when a gas is expanding or contracting. It's getting bigger or getting smaller. In order to do this, it will need to either expend some of its energy or gain some energy from its surroundings. We'll look into the details of all of this, how work, works, in the next video. That's all for now. See you then.